Suppose not. So we'll pick up where we left off last time. We were talking about hydration reactions. So if you recall, we said hydration is where an alkene, it may be substituted with some carbon groups, maybe some hydrogens, but the alkene, in essence, the overall reaction is where the components of water are added across the double bond. So the hydrogen gets added to one side of the double bond and the OH gets added to the other side. And we said if we have an asymmetrical alkene like this, one side, if the hydrogen is to that side and the OH to the other side, and the double bond is converted to a single bond, that's obviously, in this particular case, that would just be propanol. If the OH gets added to the other side, and the hydrogen over here, then that would be isopropanol. Alright, so there are two different regiochemical outcomes when I have an asymmetrical alkene. We said one of these is the Markovnikov predicted product, because that's the product where the new hydrogen ends up connecting to the carbon that already had more hydrogens. And this would be the so-called anti-Markovnikov product, which is the opposite regiochemical outcome, where the OH and the hydrogen are on the opposite carbons from where they end up in the Markovnikov addition. So last time we looked at doing a Markovnikov hydration reaction, but we showed how, because with the sulfuric acid and water conditions we used to do that, which could also be labeled as H3O plus and water, when the pi bond picks up a proton from the H3O plus and forms a carbocation, there's a possibility of rearrangement. And that leads to a mixture of products. I'm noticing that some people are having some technical troubles. If y'all can see Akua's message there, is anyone else having issues getting connected to the stream? Sounds like could be a couple individual computers having some issues. That happens to me occasionally, especially if I haven't restarted my computer in a while and it hasn't done some updates. That could be an issue. And Kristen looks like she was thinking the same thing there. Good luck with that. I wish there was more I could do for you from afar. Obviously, there's limitations there. I will be definitely recording the video though, so if you need to go back and look at part of it that you missed, you're welcome to do that later, obviously. So we were saying when we use these Markovnikov hydration conditions, if there's a possibility of the carbocation that forms when the proton's picked up by the pi bond, if that carbocation can't rearrange because it's already formed in the most stable spot, then that's fine. Those would be reasonable reaction conditions to run. But if the carbocation forms and can rearrange, it won't necessarily rearrange in every molecule because the water solvent will be right there. It might attack. And so you get a mixture of products, some rearrangement products, some forming from direct attack, and so that's a mess. We want to do clean reactions that give one desired product and a high yield. So here we're going to talk about an alternative to the acid catalyzed hydration conditions, and that alternative is the Oxymercuration-Demercuration reaction. So there are plenty of other alternatives, but this is the classic one that textbooks talk about. even though it's a bit outdated because of the fact that people try to avoid mercury due to its toxic properties. So in the oxymercuration-demercuration, it's a two-step process. You use one reagent to add an OH and a mercury across a double bond, and we're going to talk about how that works. And then the second step, different reaction conditions. So you have to do this first step and make sure it worked, and then add another set of reagents to replace the mercury with a hydrogen. So let's talk about that reaction in a little bit of detail. So the mercury acetate is the first reagent that you would add. That would be added in the presence of water. So if we look at the properties of this reagent, we see that this bond is pretty weak. Oxygen's a lot more electronegative than mercury, so it can easily, with a weak collision, provide the energy necessary to pull the electrons away and create a negative formal charge on the acetate. And the acetate has, when it carries a negative formal charge, it has resonance to stabilize that charge over both oxygen atoms. So that's one of the reasons why it's kind of a great leaving group. It can just leave and leave behind a positive charge on the mercury. So this mercuric cation, or positively charged mercury, then acts as a nice electrophile, which is the same thing as the Lewis acid. Those two mean the exact same thing. The mercury now has space in its valence level to accept and share a new pair of electrons. So if I have an alkene, which has a pair of electrons in a pi bond, they're not that stable, not held that closely to the nuclei, that can easily attack as a nucleophile the mercury that now has lost one of its two acetate groups and has a positive charge. Right? So that's the reaction that's going to be occurring first here. So what happens is, again, if we're dealing with an asymmetrical alkene where the two sides of the double bond are not equivalent, we expect to see a Markovnikov addition. So if one side already has more hydrogens than the other, I expect the OH to come into this side eventually, and another hydrogen to come into the same side where there's already a hydrogen. So we're going to explain why we get that outcome and why we don't see carbocation rearrangement. The reason for that is because we're not forming a carbocation at any point. So last time we talked about how the alkene can pick up a proton from H3O+. And so this is an alternative to that. So when the alkene came in and picked up the H+, the hydrogen that would result would add to the Markovnikov predicted side, which would be over here, to create the more stable carbocation. And there's no way for the hydrogen that just got picked up to help stabilize that carbocation because it doesn't have any electrons. What stabilizes it is the hyperconjugation and induction of these groups, neighboring groups. But what's different about the mercury is it also has a lone pair, which obviously the hydrogen doesn't have. So when the pi bond picks up the mercury or attacks is in a nucleophilic attack on the mercury, once the mercury is connected, instead of forming this unstable carbocation where the carbon doesn't have a complete noble gas configuration, the mercury can use its lone pair to form a bond there. And this is a rare example of resonance that doesn't involve side-by-side p orbital overlap. Right? When we defined resonance, we were a little bit incorrect because we said that resonance involves p orbitals overlapping side by side, creating these big molecular orbitals electrons can spread out in, and that is what happens in almost every example of resonance. Here we're going to see two examples today that are not encompassed by that description of resonance. And so here's one. So the mercury can hold the lone pair to itself, or it can share them in this bond. And in reality, neither of these structures really represents the situation. The real situation is the hybrid or average of these two structures. And that's what we see here on the next page. So after the pi bond picks up the mercury, is attracted to that positive charge to form a little bit more stable sigma bond than the original pi bond, the mercury will use its lone pair to form a partial bond with the carbocation, and that avoids a full formal positive on the carbocation. It's also a little unstable to have the positive on the mercury, and so that's why the resonance overall creates a hybrid or average that's more stable than either of those, where the positive is shared over both those atoms at the same time. And so this is what our resonance hybrid looks like. This is the best representation of what the structure will look like after the pi bond attacks the mercury. It will form a nice strong sigma bond here and a partial sigma bond there, which is like resonance. And that spreads out the formal positive over both the carbon and the mercury, so neither atom has to carry a full unstable positive charge. And since we don't have a full carbocation here, I don't have to worry about the possibility of rearrangement. It wouldn't rearrange here anyway, because it's already on the most stable carbon it can be on. But if there were like a pi bond or something over here, I might accept, if this were a full carbocation, I might expect a hydride shift to put the carbocation here where it could be stabilized by resonance. But I won't see any carbocation rearrangement because I don't have a carbocation. The mercury is already stabilizing the carbocation immediately with its lone pair in this sigma bond type resonance. So since that's a weakened bond though, and it has a lot of partial positive, the nucleophile, which would be water in most instances, because we're trying to do a hydration, it would come in there to that carbon and fully push these electrons back out to the mercury. So that would give us a water molecule there. And then that's the detail for this reaction that you need to know. The rest of the process involves a mechanism that we're not going to get into. We haven't really talked about free radicals, and we're going to talk about that next semester. So the sodium borohydride reacts in a mechanism you don't need to understand, but you do need to know the outcome of that, which is that it uses a hydrogen to basically replace this mercury acetate group, not through any of the mechanism steps that we've talked about, right? We've talked about proton transfer, nucleophilic attack, loss of the leaving group, carbocation rearrangement. What's happening between this and the sodium borohydride is different from all of that, so we're not going to be able to get into the details right now. But this gets cleaved and it gets replaced with a hydrogen. So the nucleophile would usually be a water, and it would have to be deprotonated to become neutral. But more generically, really, we could use any nucleophile because this is a nice electrophilic site. Even though it's sterically hindered, since the mercury is already kind of pulling these electrons away and it's not a full covalent sigma bond here, this has more of the geometry of a carbocation. So we should probably draw this carbon here looking a little bit more flat. And so, not a full positive, but the nice partial positive there. And since it's a little flat, since this bond right here isn't taking a lot of space, that would allow the nucleophile to come in there from behind where the mercury is relatively easily, despite the sterics. So this is an instance where we're kind of seeing something that looks like an SN2. The nucleophile is attacking at the same time that the mercury is leaving with these electrons. But since they're not really fully shared, it doesn't push these methyl groups down into a position that would crowd out the attack or approach of the nucleophile too much. So that is a way to achieve a Markovnikov hydration without the possibility of rearrangement. And that is a good answer to the first part of the first quiz question. So if you want to do a Markovnikov hydration without the possibility of rearrangement, there's a couple different ways you could do that. One is to use the conditions we talked about on Tuesday. Assuming that your alkene is like the one we just looked at, where when it picks up a proton from H3O plus, it already produces the most stable carbocation you can imagine. Then there's no possibility of rearrangement. And so then a water would come in there, and then the water would be deprotonated, and I would produce, in the end, an OH, a hydration of the alkene, right? I add an OH to one carbon and a hydrogen to the other carbon. The other possibility is the reagent we just talked about. So if I do have a situation, maybe something like this, where if the pi bond were to pick up a proton and it added to the end and I form a carbocation on a secondary carbon, it would do a methyl shift and quickly rearrange to a tertiary carbon. So if I don't want that rearrangement, after the methyl shift produces the carbocation on the tertiary carbon, the water would come in and attack there. And if I don't want that, and I actually want the water to attack here, that's where I would use the mercury acetate and water in one step, and then sodium borohydride in a second step. And through the process we just discussed, I would end up avoiding the rearrangement. I would connect OH to this carbon and a hydrogen to the other carbon. And in that case, since it's creating a new chiral center right here, I would get both possible stereochemical outcomes. Because when the alkene is flat, there's no chiral center anywhere, there's no way to force the mercury to come in from the top or from the bottom. If the mercury comes in from the top, the water will attack from the bottom, and I will get this outcome. If the mercury comes in from the bottom, which is just as likely to form the three-membered ring behind the plane of the paper, then the water would have to come in from the front, and I would end up with a solid wedge there. So I would get equal amounts of those two products in that example. So the answer here really does depend on which alkene you start with. If you start with an alkene that can't rearrange once it forms a carbocation anyway, then the acid catalyzed hydration using water would work. But if there is the possibility of rearrangement after the proton transfer step, the first step, and you want to avoid that rearrangement, this will avoid the carbocation altogether, and so you can do the hydration getting the predicted Markovnikov outcome without worrying about the OH ending up connecting anywhere else on the structure. Any questions about that? Okay, so the other part of that first quiz question was about anti-Markovnikov hydration. So we said if I have an asymmetrical alkene, what the Markovnikov reaction, if I used either the H3O plus over water, or if I used the mercury acetate we just talked about in water in one step, and then follow that up with sodium borohydride, either of those conditions would do a Markovnikov addition. And in a Markovnikov addition, the hydrogen goes to whichever carbon had more hydrogen. And so both of those, in this case I wouldn't have the possibility of rearrangement, so both compounds would give the same set of products. And that would be to put the OH group at the carbon that Markovnikov predicts. And again, I'd create a chiral center, so it would have both solid wedge and dash wedge for half the structure, so that's what the squiggle means. So if I want the Markovnikov addition, I could do either one of those reactions. But what if I want the OH on the other carbon? Right? This carbon has more hydrogens. Markovnikov predicts the hydrogen will go there and the OH will go here. But if I want the opposite, which is called anti-Markovnikov, I need a different reaction. And so this hydroboration followed by oxidation, another two-step process, has to be done sequentially rather than all at once. Those conditions will lead to anti-Markovnikov hydration. So same overall reaction. I'm still adding what was one hydrogen here, now I've got two. So I'm still adding a hydrogen to one side of the double bond, and I'm adding There's two hydrogens here, there are already two. So I'm adding one hydrogen to one side of the double bond and the OH to the other side. That's what makes it a hydration. The components of water hydrating or adding across the double bond. But since the OH is going to the anti-Markovnikov site, it's an anti-Markovnikov hydration reaction. So let's take a look at how this reaction works in a little bit of detail. So when we do this reaction, what we observe experimentally, specifically, is a regiospecificity. There's stereospecificity. There are specific stereochemical outcomes that are observed experimentally when I run the reaction with these reagents, and other stereochemical outcomes that are not observed. So what SYN means is that I have the groups that are adding across the double bond added to the same side spatially. Right, so the hydrogen and the OH both having solid wedges or both having dash wedges, those are SYN outcomes. It's similar to the word cis, except since they're not identical groups, I can't use that term. Cis is only when I have identical groups on the same side of a double bond or a ring. So when I add my two groups to the same side of the double bond, we call that SYN. I don't see the anti. Right? We talked about anti. Anti, if you look at a Newman projection, is where one group on one carbon and the group on the other carbon are pointing in opposite directions. One would be pointing out at you, one would be pointing away. So if the hydrogen and OH were to add in a way that was anti, the hydrogen would be coming out at me, the OH would be pointing away, and vice versa. But I don't see these products. I don't get that. So we want to be able to understand why the reaction only produces certain stereochemical outcomes and not other potential outcomes, right? So if I just look at the structures, there's nothing especially stable about these structures or unstable about these structures. So thermodynamically, there's no reason why the products down here would not form. So it must have to do with kinetics, it must have to do with the mechanism. There must be some reason why the collisions that are necessary don't produce the hydrogen and the OH on opposite sides of the carbons that they're adding across. So in the mechanism, what we have here in terms of the BH3 is a molecule that's kind of similar to a carbocation, right? BH3 is trigonal planar. The boron doesn't have a lone pair. To make it avoid a formal charge, it has 3 bonds and no lone pairs. And those bonds would be in the plane, just like the 3 bonds on a carbocation are in the plane. It has an empty p orbital, just like a carbocation has an empty p orbital. The only difference is the boron has 1 proton less in its nucleus than carbon has, so it doesn't have an overall positive charge, so it's a lot more stable than a carbocation. So that's the nice thing about boron. It's unstable enough because it doesn't have a noble gas configuration and it has an empty orbital that any kind of nucleophile with the lone pair could come in and start overlapping with this orbital and form a 4th bond. But it's not so unstable like a carbocation that I can't buy it from a chemical company and store it for a little while. Carbocation is super unstable. It'll react with anything that has a lone pair that can come in here and share. So it's hard to store that in a way where it won't eventually start to react over time. So I can get my hands on boron. It's like a carbocation. It's a great electrophile. It's not as good as an electrophile as carbocation because it doesn't have a charge, but it has an empty orbital that can accept more electrons. Right? And that's the theme we have here. If I have a reaction I want to do with a pi bond, it's the pi electrons that aren't that stable. And so they are easily attracted to nuclei and to forming sigma bonds with those nuclei. To mention one other thing about boron, individual molecules of boron, as we said, they have that empty p orbital, so they don't have a noble gas configuration, so it's a little bit unstable. So interestingly, when 2 boron molecules come together, 2 BH3s come together, they can actually quickly swap hydrogen. And that, when you look at the structure during the swapping of these hydrogens, it creates something called banana bonds, which is a situation where I've got 2 electrons total shared in a cloud over 2 borons and one hydrogen at the same time. So this is also like resonance, but it's like sigma bond resonance. Right? So instead of having pi electrons shifting in an orbital over multiple atoms, these two sigma bonds that aren't really either full bonds, because I don't have two pairs of electrons to make two bonds, I only have one pair of electrons here, they're going to be able to spread out over the cloud connecting over three atoms. So these two borons still only have 6 electrons around them, but since they can do that up here and down here, it gives the borons more of a complete noble gas configuration. And that stabilizes those boron atoms a lot. And so what we're going to be working with instead of just straight up boron, which would be a little bit too stable to react because of the stabilizing banana bonds that would form there, is the boron is complexed with THF, which is a 5-membered ring that includes an oxygen. And so what happens here is the oxygen will start to share electrons in there and form a covalent bond. But then the formal charges that are created make the oxygen very easily pull those electrons back and go back. So that creates an equilibrium where some of the boron molecules are stabilized by forming a 4th bond and completing their noble gas configuration. Some of the boron molecules at that moment won't be reactive toward the alkene, but since it's in equilibrium, there will be some concentration of reactive boron molecules, and it will be a little bit lower, so they won't all join together to form these more stable banana bond structures. So that provides a small but constant concentration of boron molecules in solution that can react with the alkene molecule to start off this anti-Markovnikov hydration reaction. So what role is the BH3-THF likely to play in the reaction? Well, really it's just temporarily stabilizing the boron with the noble gas configuration, and when the oxygen leaves, because it's way more electronegative than boron, especially with the charges that are here, positive really strongly attracts these electrons, the negative is repelling them, so they'll very quickly go to the oxygen if a collision occurs, and I'll create this boron. And so what role does the boron play? It's an electrophile. It attracts the pi electrons from the alkene, and that's the first step of the mechanism between those molecules. So what happens is there's an electronegativity difference between boron and hydrogen, a rare situation where hydrogen's bonded to something less electronegative than it. So that creates a very slight partial positive here, a very slight partial negative there. Oops, wrong direction. So used to hydrogen being less electronegative. Like negative there, slight positive here. And so the very slight partial positive on the boron helps it to attract these pi electrons. And so also the fact that it has an empty p orbital. Oops. So the empty p orbital here and the slight partial positive makes a decent enough attraction for these pi electrons. So when a collision occurs here, I imagine these pi electrons coming out to form a bond to the boron. If the electrons swing out here and start to form a bond to the boron, they'll be pulled away from this carbon, which will take on a partial positive. And that positive would become a carbocation, except for the fact that the boron hydrogen electrons come in there and form a new bond. So I'm forming 2 bonds and breaking 2 bonds at the same time. This is pretty uncommon to form a 4-membered ring like this because of the bond angles, and to break and form 4 bonds at once. So it's a pretty decent transition state that this has to get through for this reaction to occur. But it's not prohibitively high, so there will be collisions that allow this to happen. And this is a really key part of the mechanism, because this first step is the step that determines the overall stereochemical outcome that we're talking about over here. Right? The fact that the hydrogen and the oxygen always end up on the same side, both solid wedges, both dashed wedges, instead of anti, they always end up syn, is because of this step. The boron is adding to one carbon at the same time that the hydrogen is adding to the other. And if I think about the orientation with which these structures approach one another, this carbocation or this alkene is flat, and so the BH bond will either come down on top of it, so that the hydrogen and the boron come down on the same side from the top, or easily the BH bond could approach from the bottom, which would put the hydrogen and the BH2 group again on the same side, but on the bottom. So I've converted this pi bond into more stable sigma bonds in one step. I've avoided a carbocation intermediate that's really unstable, so this mechanism looks pretty good. And the fact that the BH bond is breaking at the same time the new bonds are forming means that the boron and the hydrogen have to approach the alkene from the same side, and they end up either both in the front or both in the back. So that will happen on one BH bond, and now I've still got two more. So it will happen on another one. The boron, oops, drew that one the wrong way. Try it over here. The boron will accept electrons from the pi bond, and these electrons will come in here. And then it'll happen again. The boron will accept electrons from the pi bond, and these electrons will come in here. And so eventually, this R group gets connected in three different locations, right? I'm adding three different BH bonds across the pi bond three different times to create this intermediate. So let's look at this first step a little bit more, because you're probably wondering, well, why does the boron add to this carbon and the hydrogen to this one? Why not the opposite? Why not have the structure flip over and have the boron up here? Well, there's two reasons for that. I can imagine it occurring if the electrons come to the boron. These electrons could come in there. So I could add the boron to the more crowded site and the hydrogen to the less crowded site. So let's take a look at that step in a little bit more detail, right? So here's the first step. So there are really two reasons why the boron adds to this side and the hydrogen adds to the other side of the pi bond. Right? Markovnikov would have predicted that the hydrogen would add to the side where there's already more hydrogens. Right? So that's why this reaction is called an anti-Markovnikov addition, because it doesn't give the products Markovnikov would predict. The hydrogen is not adding to the carbon that already had more hydrogen. It's adding to the carbon that had fewer hydrogen. So that's anti-Markovnikov. Why does it do that? Well, one reason is because of sterics. Right? This side's more crowded, and a hydrogen is smaller than a BH2 group. So if the hydrogen approaches the side that's more crowded, I don't have as much steric hindrance during the transition state. The transition state will be lower in energy, and it'll happen that way more often. And the other reason is electronics. So if the electrons here were to move this way and connect the boron to this carbon, which is not what should be happening, if that were to happen, the electrons would be pulled away from this primary carbon, and a partial positive would start to form on our primary carbon, which can't be stabilized well by induction and hyperconjugation. So that's not what we see. Alternatively, we see the pi electrons moving out to the boron away from the site that can stabilize the carbocation more. Right? So in other words, when the pi bond breaks, it starts to form a sigma bond with the boron in the less crowded site due to sterics, but also it starts to form a sigma bond with the boron pulling electrons away from the carbon that can stabilize the positive better when those electrons are pulled away from it, and then that starts to attract the hydrogen in there. So to avoid forming a partial positive on the carbon that can't stabilize it as well, which would also be a higher energy transition state and happen less often, what we see is the boron pretty much always adds to the carbon that's less substituted, and the hydrogen adds to the other one. So this explains the anti-Markovnikov outcome that we get. So make sure that you can explain that if you're asked about it. All right, so what happens next? So we had this structure here. We just saw how that formed, right? So the R group, just to recap, is some kind of alkene, and the boron and hydrogen bonds add across that. Right, the boron accepts the electrons as a partial positive starts to form. The hydrogen brings its electrons in to avoid a carbocation. So what happens is then the boron and the hydrogen are both now connected there. And the boron would do that with multiple structures. So there'd be two other R groups there. Right? So that's what this structure here is meant to show. So that's the first step. Right? When we look at the reaction conditions, the first step is just to add the BH3 and BHF. That produces the molecule we just saw. The second step is added later. After that happens, the H2O2 and NaOH are added. Right? So I don't want these added right away because I don't want the hydrogen peroxide, which is a very unstable reactive molecule, or the NaOH. I don't want those reacting directly with the alkene. Right? So I want the BH3 reacting with the alkene. So I add that with the alkene first. That's step one. And that produces this structure here, which is the same as this one. Then in step two, the hydrogen peroxide and the NaOH are added together. When they're added, they react together, so a quick proton transfer occurs, producing hydrogen peroxide into this peroxide ion. Now that's a good nucleophile. So that attacks the boron. Right? So if it attacks this boron, it's the same as showing it attack this boron. Oops, sorry, it's not a boron. This boron here. Right? The boron doesn't yet have a noble gas configuration. So it can accept a new bond, and so it does. It forms a temporary negative charge. That's a little unstable, and these carbons are more electronegative than the boron. Right? So what we have here is this boron connected to the carbon, and it would have that occurring in 3 different positions. And then this O2H would come in. So this R group now pulls the electrons away from the boron and uses them to bond to this oxygen, and that pushes out an OH minus. So this oxygen-oxygen single bond is especially weak. Breaking that bond requires very little energy, and then forming a new bond is more stable, so that releases energy. So the fact that this oxygen-oxygen bond eventually is breaking is an exothermic step, despite the fact that it releases a relatively unstable OH minus. And so that's what favors this step to occur. So the migration of this R group over to the oxygen now puts it on the oxygen. So now I've got a structure that looks like this. So the oxygen now is bonded to this carbon because it moved over there and it took these electrons and brought them over to form that bond. So if the boron was connected to this carbon with a solid wedge, and now these electrons suddenly jump over and bonded to the oxygen, it remains a solid wedge. So this is like the opposite of an SN2. Right? So it's not like the oxygen is coming in from the backside and pushing the boron out. The boron is not a leaving group. It can't attract the electrons nearly as well as carbon. So it's the carbon that takes the electrons, but it can't stabilize them as a lone pair with a negative, so it immediately starts to share them with the oxygen because it's right there, right nearby. And that retains the R. So this is not a chiral center, but if it were, it would retain the RRS configuration at this chiral center after the migration. And so since the hydrogen and the boron came in on the same side, now the oxygen ends up exactly where the boron was. And so the rest of that mechanism, the oxygen is now connected to the carbon, so the OH minus comes into the boron, and then that pushes out the oxygen, which then picks up a proton and produces your product. Right, so the rest of these steps end up producing that carbon bonded to an OH. Right? Now I have an OH there, and the hydrogen added to the same side. So I get syn addition because the step where the oxygen comes in replaces the boron in the exact same spatial positioning. And the boron and the hydrogen came in together and had to add to the same side. So that's a pretty complicated mechanism. It's pretty unlikely I would ask you to go through every step of that in an exam answer. But there are key aspects of the mechanism you want to be familiar with so that you can use them to explain the outcomes of the reaction. Right? So those three key things. Let's just recap them one more time. So we said the one thing is the regiochemical outcome, the anti-Markovnikov regiochemical outcome. And that's created for two reasons. Because the boron is a little bit more sterically hindered than the hydrogen, I expect the hydrogen to come into the carbon where it's more crowded. And because the electrons are moving out to the boron, since it carries a very slight partial positive, they're going to be pulled away from the carbon that can hold the partial positive more effectively, and then that's going to attract the hydrogen in. So that helps me to predict which side the boron's going to add to, which side the hydrogen's going to add to. When that occurs, I have to think about the stereochemistry involved. The boron and the hydrogen approach together, either both on the top or both from behind. So that gives me two possible outcomes there in terms of the stereochemical outcome. So either the boron adds to the same side of the hydrogen with both pointing out at me, or it adds to the same side as the hydrogen with both of them pointing away. And then the rest of the mechanism basically replaces those borons with OH groups. So if I'm forming a chiral center, the stereochemistry of the boron will be, which is eventually going to be replaced with an oxygen, will be on the same side as the hydrogen if it's got a solid wedge, or it'll be on the opposite side as the hydrogen if it's on a dashed wedge. In this particular case, though, I only form one chiral center, so I get both outcomes, one with the OH with the solid wedge and one with the OH with the dashed wedge, and that's what that squiggle is meant to indicate. The squiggle here implies that the OH is coming out at me with the solid wedge in half the molecules and pointing away with the dashed wedge in the other half of the molecules. And that's because of the flat geometry of the alkene, right? There's no spatial chirality to this alkene. There's no reason why the boron and hydrogen would come in from the top any more than they would come in from the bottom. So I end up with the OH on the top and on the bottom in equal quantities. So this slide illustrates a situation where the syn addition is relevant stereochemically. Right, so as we said, because the boron would come into the less crowded side for both sterics and electronic reasons, and the hydrogen will come into the other side, and because this addition now is going to create two new chiral centers once the addition occurs, I have to recognize that as the electrons come out to the boron and the hydrogen brings its electrons in, they'll add to the same side, either both with dashed wedges or both with solid wedges. I could imagine two other stereochemical outcomes where the hydrogen has a dashed wedge, and once the boron's replaced with an OH, it ends up with a solid wedge. But I would not form that because that's an anti-addition. So I'm doing anti-Markovnikov. I know it's a little confusing. We're doing anti-Markovnikov because we can predict the boron and hydrogen add to the carbons of the double bond that are the opposite of the Markovnikov rule. But it's not anti-addition because anti-addition implies that the groups adding across are spatially 180 degrees away from one another, or anti. So we're only getting the syn addition products. We're not getting either of the two anti-addition products that we could imagine drawing. Right, so the other one would have the hydrogen pointing out at me and the OH pointing away. I'm not going to see that because when the boron and hydrogen add to the same side, wherever the boron ends up, it gets replaced with the OH without changing the configuration at the carbon, as we saw in the mechanism. So make sure you can explain that and use it to predict the outcome of reactions like these. So in this reaction here, I'm thinking about which side the boron is going to add to. I expect it to add to the side of the double bond that's less crowded, and the hydrogen is going to add to this side. They both have to come in from the top together or from the bottom together. So here though, I am starting with a molecule that's already chiral. This methyl group is a bit crowded and it's probably blocking the top face a little bit. So here I might not get the BH3 coming in from the top as much. It might be blocked out by the methyl group. So I expect when the pi electrons come to the boron and the hydrogen puts its electrons here, and then the boron's replaced with an OH, the product I expect to see there mostly will have the boron and hydrogen coming in from the bottom, which will force this methyl group up. And then the boron would be replaced with an OH eventually through the mechanism we saw. So that should be the major product I would expect. The methyl group's not extremely bulky. It's not going to crowd out the top of the ring too much. So BH3 is a relatively small molecule. It could come in from the top sometimes. And so I would also expect to see some of the product where the boron comes in from the top and is eventually replaced with an OH. And the hydrogen would have to come in from the same side. And that would push this methyl group back, and this methyl group would still have a solid wedge because nothing's happening at that site. So I would get those two products, and one would I would probably have a little bit more of than the other because the methyl group crowding things out. Same situation here. I've got an asymmetrical alkene. There's one hydrogen here. There's none over here. And so I expect the boron to come in on the side that's less sterically hindering, that will allow the electrons to connect to it, leaving a more stabilized partial positive that the hydrogen can bring its electrons to and attack as well. And then, so that will give me a 6-membered ring here. So we'll just draw the flat looking one, and a 5-membered ring here. And so the boron either comes in from the top and is then replaced with an OH in that spatial positioning, in which case the hydrogen would come in from the same side, or it would come in from the bottom, which would put it with a dashed wedge, and the OH would also have to add a dashed wedge. Oops, it should be a hydrogen. So the OH and hydrogen add to the same side. That's what we mean by syn addition. So now, any of those could qualify as a good example of a syn addition anti-Markovnikov hydration. Right? So the conditions there are the BH3 THF in one step, and then in the second step, the hydrogen peroxide and NaOH. So any alkene, maybe it's just cyclohexene, would give me, well, maybe I put a methyl group here so I can show the difference between Markovnikov and anti-Markovnikov, make it asymmetrical. So I would expect the products that result to be putting the hydrogen at this position, the anti-Markovnikov outcome, and the OH at the other position, and they would have to add on the same side of the ring. So the OH and the hydrogen would be on the same side, pushing the methyl group back. Half the time, since it's flat, there'd be no reason to predict the BH3 would come in from the top more often than from the bottom. So I would also get a situation where when the BH comes in from the bottom and the OH replaces the B, it gives me the other syn addition product. So I only get syn addition, and I only get anti-Markovnikov addition. Alright, so that's it. So there are 3 different reactions you should know, and you should know a little bit about the mechanisms of each one of them, and you should be able to get through the full mechanism for the acid catalyzed hydration reaction. But there are 3 total hydration reactions that you should be able to recognize when each of the 3 sets of reagents are necessary and what the products should be from each of them, as well as discussing the key mechanistic steps that result in the regiochemical and stereochemical outcomes for those reactions. So the next addition reaction we're going to discuss is hydrogenation. So this is a simple term, hydrogenation. So it's a process of adding hydrogen across the double bond. So the easiest way to do this is just to use hydrogen. The hydrogen molecule, it could collide here. So similar to the last mechanism we saw, if the hydrogen molecule accepts the pi electrons and then uses its sigma to form a new bond there, I can add the two hydrogens across the pi bond. If I don't use any catalyst, the process is extremely slow. And so if we're thinking about the reaction coordinate diagram, without the catalyst, it requires a very large amount of energy in that collision. And that almost never happens. I would need to add a huge pressure of hydrogen. So I'd have to put this in a vessel that can withstand a massive pressure and pump in a very large number of moles of hydrogen so they're colliding really hard. I would need a really high temperature to provide the kinetic energy to get to that transition state. So instead, we use a metal catalyst. And so what's happening here, come back to that, is the metal catalyst provides a surface with loosely held electrons, and those electrons can shift around. So these other pi electrons can come in and form some nice London forces, right? When this electron cloud comes in here, the electron cloud that's already on the metal surface can kind of shift away and create some areas of partial positive to attract the negatively charged pi electrons here and bring that in and form an attraction. It also forms the equivalent of weak covalent bonds with the hydrogen. So H2, not the most stable molecule, not super unstable, but if it collides with the surface of the metal, the sigma bond can break, and the metal's valence electrons, so it's a neutral metal, it has loosely held outer valence electrons, they can start to be shared with the hydrogens. In addition, they'll also use the sigma electrons here between the hydrogens to form some bonds. So these hydrogens are basically just sitting on the surface, waiting for this pi bond to come in there and form an attraction to the surface of the metal. So in this case, the metal facilitates the reaction by increasing the number of steps in the mechanism. It's not a one-step process. And by forming attractions to the reactants. I've got an alkene, I've got hydrogen, the metal attracts to both of them. So during the collision, where the hydrogen starts to add across that pi bond, it's much more stable to do so on the surface of the catalyst. And since the alkene can only come in from one side, right, this alkene is flat, it's going to like as a pancake, it's going to sit flat on top of the surface of the metal. So the side that comes down facing the metal is the side that the hydrogens add to. Both hydrogens will add to the same side. So this is another example of a syn addition. They're adding to the same side because that's the side that happened to collide with the surface of the metal. I've got this flat structure like a pancake. It's going to sit down flat on the metal. It can only sit down on one side or the other. It can't be both, right? I can't add hydrogens to opposite sides because they're both adding to the side of the alkene that sits down there. And so that's why I get syn addition. So the mechanism here you wouldn't have to draw because it's a complicated mechanism that involves the surface of the metal. You should know that the metal attracts the reactants during the collision, so the transition state in the slow step is much lower than it would be otherwise, and that's how the catalyst speeds up the process. And you should also know that the catalyst facilitates the hydrogens adding to the double bond, but whichever side or whichever face of the molecule sits down on the catalyst, the hydrogens would both add to the same side. Not necessarily at the same time, but they'll add to the same side. So if they both come in from the top, it'll force the R groups down. Right? And the hydrogens will be here on the same side. That's syn addition. They're adding to the same side stereochemically. Spatially, if they are able to connect on the other side of the structure, then they would both have dash wedges. I don't see the other possible stereoisomers. So again, it's a stereo-specific reaction where I don't see the other stereochemical outcomes. I don't have one of my R groups up and the other back. because that would require one hydrogen to come in from behind and the other hydrogen to come in from the front. I just don't see that. Once the alkene sits down on the surface of the metal, only the side that sits down the hydrogens can add to. So they have to add to the same side. They cannot add to opposite sides. So I don't see the other outcome. So again, another syn addition reaction. So if I'm asking you to predict the products of an alkene being hydrogenated in the presence of a metal catalyst, the metal catalyst could be platinum or nickel or palladium. Now, palladium, from my experience, is the most common and effective. Platinum is the more expensive. So the two hydrogens would have to add to the same side. And that would push the two methyl groups onto the same side. So I see these two reactants. So what's the relationship between these two? They're identical. If I flip one over, it'll be exactly able to line up superimposed on the other. So I don't need to draw both of them. So I get one stereochemical outcome. I'm not going to form any of this or any of this. There's no way in this process for the two hydrogens to add to opposite spatial sides of the pi bond. So since I'm not forming these, the only product would be this meso compound. It's a meso compound because there's a plane of symmetry. So I still have two chiral centers. This one here is R. This one here is S. Even though there are chiral centers, it's an achiral molecule due to the mirror plane splitting it in half, where one half the molecule is a reflection of the other half. So that's what we mean by meso compound. Two chiral centers. I can also do this reaction with a homogeneous catalyst. So we talked about this metal catalyst. It's a heterogeneous metal. That's because it looks like a powder, but it's just tiny, tiny, tiny chunks of metal. And we want it to be a powder, right? I wouldn't put a big chunk of platinum in my reaction, because then only when the alkene comes down on the surface would it be able to react. I want to maximize the surface area. If I have a chunk and there's only a little bit of surface area and all the platinum atoms are in the middle of the material, the bulk of the material, the alkene can't access it and collide, that doesn't do me much good. So if you buy these catalysts in the solid state, they come as powders, and the powder provides little tiny chunks of surface area so this collisions can occur as often as possible. Still though, even with a powder, on a microscopic scale, if I look at a tiny particulate of powder, still most of the atoms are in the inside. The surface area is greater than it would be if it was a chunk, but I can still only do the reaction on the surface, and so all the atoms that are in the inside aren't able to act as a catalyst, and I'm wasting material, especially if it's something expensive like platinum. So alternatively, a lot of chemists focus on heterogeneous catalysts. And so instead of using a chunk of metal where my metal atoms are all stacked together in rows and columns, and a lot of them are on the inside of the material and can't ever be accessed to act as a catalyst, if I separate the metal atoms and connect them with ligands that make the catalyst now soluble, now every single atom is available to help facilitate the collision between the reactants. So that's the advantage. No wasted metal. Nice collisions. The metal is active in solution. It's a solute. It's in the liquid, bouncing around, and so the collisions here are facilitated by dissolving the metal instead of having it sit on the bottom as a powder. And so this reaction works in basically the same way. The other advantage of homogeneous catalysts is the ligand that you use can be chiral. And that can then create a spatial arrangement that makes the alkene more stable when it collides with one side than on the other. So a chiral catalyst produces one desired enantiomer versus another. Right, so what we mean by that is, if I have my metal atom and my hydrogen starts to form a connection to it and the alkene comes in to attract to that metal, if the metal has a ligand, like some of these ligands we see that have groups positioned in a spatial direction, it can control the most stable pathway through which the alkene comes in and grabs the hydrogen. So if one face of the alkene were to come in and be blocked by the ligand, the alkene would have to flip over. And then when it comes in, the hydrogen almost exclusively gets added to one side. So if one spatial orientation where the alkene is approaching the hydrogen is a little bit less stable due to being blocked by this chiral ligand, then the other face of the alkene coming in doesn't have that problem. It's going to be lower in energy. And so we can create a difference in energy for one stereochemical outcome versus the other, and that gives me an enantioselectivity for my reaction. So why would someone ever want enantioselectivity? Well, if we're using this reaction to produce a drug, a pharmaceutical, we talked about this when we talked about chiral compounds. If I'm producing a molecule that's chiral as a drug, and I give a patient both the chiral drug I'm interested in and it's an enantiomer, well, the enantiomer won't interact in the body in the same way because all the molecules in your body are chiral. They all have specific spatial arrangements of the atoms, and so this drug would have to go in and interact with some protein or enzyme in some specific spatial way, and the enantiomer wouldn't be able to do the same. So not only would the enantiomer not have the same medicinal effect because its spatial positioning of its groups are different, it would also probably get involved somewhere else in the body in some undesired way, maybe causing some terrible side effects. And that's been seen throughout medical history with terrible results for some people. So in modern medicine, we avoid racemic mixtures. We make sure that if one enantiomer of a mixture is medicinal, we don't put the other one in with it because we don't want to complicate that and add anything in that would potentially be harmful. So it's a huge advantage to do a reaction like this. So this is an example. I'm not going to get into the specifics of the structure too much, but this is a chiral structure. Okay, so these two phosphorus atoms bond to the metal that's doing the catalysis. And the spatial positioning of these rings is specific so that when this alkene comes in and sits down on this metal with the hydrogen attached to it and the hydrogen adds across the alkene, the hydrogen will always, 95% of the time, it will come in from one side. Actually, it's more than 90. It's 97.5% of the time I will get this specific enantiomer, and 2.5% will be the other enantiomer. So that's 95% enantiomeric excess. So what that means is the hydrogens will always be added underneath to push the methyl group forward. That produces the syn addition that we just said. The hydrogens always add to the same side of the double bond, but it also forces the methyl group out of that plane. And if this is the enantiomer we want, then this chiral catalyst has helped us make that. So that's the other advantage of a homogeneous catalyst, one that's able to dissolve in solution, is if I use ligands on the metal that bring it into solution that are also chiral, depending on the specifics of the ligand and the spatial positioning of things during the collision, it can promote the pathway that produces one enantiomer selectively over the other, and then I don't have as much of the other enantiomer to remove in order to make this molecule available as a pharmaceutical. I have to have at least one reactant or catalyst that's chiral to get a selective reaction like this, or an enantioselective reaction. So as long as my catalyst is chiral, I've got the possibility of producing one enantiomer a lot more than the other, right? The other enantiomer would obviously look like this, where the methyl group has a dashed wedge because the hydrogens came in from the front. And so that would be blocked by this chiral ligand, forcing the hydrogens to come in from behind, pushing the methyl group forward, giving me the specific enantiomer that I'm trying to synthesize. I don't want to get into too much of that. I probably won't ask you about it on the exam, but that is starting to give you hints about what you would see in a more advanced organic class. So here we're back with a standard powder metal. It's a heterogeneous catalyst. It's not homogeneously dissolved in solution, but the alkene and the hydrogens can still sit down on the surface of that metal. In this case, since I've got a methyl group here kind of blocking the front, we saw this molecule before, it'd be more likely for the hydrogens to come in from behind. So when those hydrogens come in from behind, that would push this other methyl group forward. I get a syn addition, both hydrogens add to the same side, and that would be my major product. Alternatively, since the hydrogen molecule is small, it might come in on the top. But if that methyl group gets blocked by the platinum, that reaction might not happen as often. That's why it's going to produce a minor product. So if some of the hydrogen does come in from the top, though, that would push this methyl group back. Oops. So this methyl group is pointing up, and no reaction is changing the chirality of this center. But when the hydrogen comes in from the top, it would force this methyl group back. So that would be my minor product compared to the major cis. I'm still getting the hydrogens adding on the same side. So anytime you do hydrogenation, always remember the hydrogens should add to the same side of the pi bond that they're adding across. Likewise here, that pi bond, which would have been right here, the hydrogens add to the same side of it. So that pushes, no, that would leave one hydrogen here, and the other product where the hydrogens add to the same side will look like that. So this hydrogen is already putting down. It has a dashed wedge. So what's the relationship between these two structures? Well, they each have two chiral centers, one here and one here. So if the configuration at one center is the same in structures, but the configuration at the other center is different, that makes them a pair of diastereomers. So I would get both these diastereomers. It's hard to say which I would get more of, but I would definitely get significant amounts of both of them, because it'd be difficult to control which side of the alkene comes down on the surface of the platinum to have the hydrogens added across it. All right, so that's hydrogenation. So we did hydrohalogenation on Tuesday. We did some hydration on Tuesday. We looked at more hydration today. We looked at hydrogenation today. And so now we're going to talk about halogenation. So this is just the word halogenation. So it's the process of adding halogen across a double bond. So here the reactant is a halogen, and both of the CLs of this halogen molecule are going to add across the pi bond. So halogenation is also a very useful reaction. I can convert an alkene into a dihalide, molecule with two halides, or two chloro groups in this case. This is a key, this particular example, this specific reaction where I take ethene, which is commonly known as ethylene, and I add chlorine across the pi bond, I get dichloroethane. And dichloroethane is a precursor to polyvinyl chloride, which is a polymer that's used a lot in plumbing and and pipes and tubing. Right? So what happens is you take petroleum that you get out of the ground, you isolate the ethane that's present in that petroleum, you add chlorine, you make this molecule, and then how do I get from this dichloroethane to vinyl chloride? So it's obscured there. Let's draw it down here. What reaction would need to happen to remove one chlorine and remake a pi bond? Well, that would be an elimination reaction. So for every mole of this, if I add 1 mole of a base, like maybe a terbutoxide, that would do an E2 reaction. I'm talking about elimination. It could come in and pick off whichever proton becomes antiperiplanar to one of the 2 leaving groups, and that would make a pi bond and leave the other chlorine still connected to the pi bond. And so that's called vinyl chloride. And then you make that into polymer chains. When you make vinyl chloride into polymer chains, you get a long chain of carbons, and there's a chlorine every 2 carbons. That makes the structure more rigid, but also gives it a little bit of flexibility and makes it really good for piping. It's a very stable structure. It won't degrade or break down over time very easily. So let's take a little more detailed look at this halogenation reaction. What we find is it's relatively effective. We get decent yields of product when we use chlorine or bromine. The iodine is a little bit more stable. It doesn't react as quickly, and so that makes it less practical. And the fluorine is just a really reactive compound or a chemical, so we really avoid using that. It just reacts really strongly. And not only will it react with the pi bond, it will start to replace the CHs with CF. So if we only want to do an addition across the pi bond and not affect any other part of the molecule, we can't work with fluorine. Plus, normally we want to add bromine or chlorine anyway because those are good leaving groups. And by adding those 2 across the pi bond, now I have ways where I can further manipulate the structure and add a nucleophile or make another pi bond somewhere else, start to connect structures together and increase the complexity and value of my chemicals. So what do we see here experimentally? If I take cyclopentene and I add a halogen, either Br2 or Cl2, what I see here is only anti-addition. There's no addition. So I don't get any of the potential products I could imagine getting where the bromines both add to the same side, which would be identical to the one where I have them both as solid wedges. I don't see that. And so again, that's going to have to be explained with the mechanism. It does suggest that the 2 BRs are probably not coming in on this at the same time. Right? If I had a flat ring and the BRs are coming in at the same time, it would be difficult for one to come in from the top and the other somehow come in from the bottom. Right? They would have to collide on the same side. If they collide on the same side, I would get them on the same side. But since I don't see that form experimentally, I know that this is not likely to be a one-step process. It's more likely to be a multi-step mechanism because one bromine is going to come in first, and then the other one's going to have to come in from the other side to get this anti-product where the 2 bromines are pointing spatially in opposite directions. So the mechanism for that is what we're going to talk about next. So if I'm using chlorine or bromine, what are those chemicals like? Well, they're nonpolar, but they're quite polarizable, right? Whether it's chlorine, the chlorine molecule has 2 core layers of electrons and its valence electrons are in its 3rd level. Or if it's bromine and there are 1, 2, 3 layers of electrons followed by the valence electrons, there's lots of shielding between the valence electrons and the nuclei. So those valence electrons can easily shift around, and that makes the molecule polarizable. it creates a situation where if the electron cloud randomly shifts to one side, that side will be more negative, the other side will be more positive. And whichever side is temporarily positive makes that side electrophilic. There's a, if the nucleophile is fully negative, there's an ion-induced dipole attraction between the full negative and the partial positive. And this positive is electrophilic because it can attract the electrons from the nucleophile. It's also nice and electrophilic because the other bromine would make a great leaving group, right? The bromine atom is great at stabilizing a negative charge. So if this nucleophile comes in to connect to the positive side, that would be temporarily positive, the other side can pull away the shared electrons, right? So that's what we see down here. So this is what our first step is going to look like, sort of. We're going to see how it's not quite going to capture what's happening in this reaction. So if I imagine the same theme we've seen in all these addition reactions so far, which is where the pi bond acts as a nucleophile or a base, either way, using a lone pair to pick up something, either a proton or something else. In this case, instead of picking up a proton or the mercury that we talked about or the boron we talked about earlier, it's going to be attracted to the bromine. So again, the pi electrons are not as stable as the sigma electrons. And so that's what's helping this first step occur. So if we imagine the way that we just talked about it, where the polarity of the electron cloud randomly shifts to one side to create this temporary dipole or induced dipole, and the pi bond, which is an area of negative charge, it's not very close to the nuclei, were to be attracted to that bromine, it could attack as a nucleophile. And the bromine here is an electrophile. And this is a great leaving group. So we have a nucleophilic attack and a loss of a leaving group. If that were to happen, as the electrons get pulled away from this carbon, maybe they're connecting to the bromine over here on this side, that would create a carbocation. And we know from experience a carbocation is flat, its p orbital is empty, and the Br just left as a leaving group could then come in from the top or from the bottom with equal probability. If that were what was occurring, this top approach would produce a situation where both bromines end up on the same side. But we said that does not occur. We don't see that. So that means that this mechanism must not be correct. Even though it makes sense, it doesn't give the experimental outcome that we observe. We never observe syn addition. We only ever see the second bromine coming in from the opposite side that the first bromine was added to. So this mechanism, as it's shown, does not match the stereochemical outcome of the reaction. The reality is we only get anti-addition, not syn. And this mechanism would predict we would get equal amounts of both, so it can't be correct. So further investigations of the mechanism suggest something a little bit different. So we actually see in this reaction, the mechanism that you need to be able to draw if I asked you a question about it, is the pi bond connects to the bromine at the same time, since the bromine has a lone pair, very similar to the mercury step we talked about in the beginning today, that bromine would use its lone pair to make a second bond. So I form a three-membered ring. This is very similar to what we said could happen if mercury adds across the pi bond. With the case of the mercury taking on a positive charge, just like the bromine. And if you recall the mercury acetate reaction, water attacks to open that up. So if the mercury is occupying one side, the water would have to come in from the other side. And then when this opens, the mercury would still be over here on this side. And then the mercury would be replaced by a hydrogen. So that's why we got anti-addition. So this is almost the same thing. when you form a three-membered ring that's positive, that's going to be attacked, it's got to attack from the opposite side from where the leaving group is located, similar to an SN2. So that's what happens here. Two pairs of electrons. The bromine is attacked, it attacks back to form the three-membered ring. And now either of these carbons is going to have a partial positive because the electrons are pulled away. The bromine could attack either one of them because it's symmetrical, but it cannot come in from the same side that the bromine that's already existing is on. It's too crowded with electrons over there. It has to come in from the opposite side, either there or here. And that's why I get anti-addition, because whichever side it comes in on, the bond that's already there breaks, and so that produces one bromine, the one that was already there in that three-membered ring. That bromine stays on one side, and the other bromine came in on the other side, ends up on the other side, and that's why I get anti. So only anti is observed. Why? Because the Br minus has to attack on the opposite side from where the three-membered ring forms. In this particular example, it would produce a pair of enantiomers. Because as we said many times, an alkene is flat. There's no reason why this Br2 would have to come in from the top. So it could have easily come in from the bottom. If it attacks on the bottom and then gets attacked back, and this acts as a leaving group, that would give the bromonium forming below the ring. And if it were blocking the space below, then the other bromine, or the bromide that's acting as a nucleophile next, would have to come in from the top. It could come in from the top here or the bottom, or the top over here. And so that would produce this one and this one. Oops. Ignore that. So those are the same two compounds that we see over here. Right, so two possible stereochemical alkyls. And while they look very similar, and indeed they are mirror images, where this one's reflecting over here, this bromine's reflecting over there, they're not superimposable, right? So if you made a model of both of these, you'd find you wouldn't be able to make them look identical no matter how you rotate things or flip things over in space. So that's why they're enantiomers. So again, the unfortunate part here is I can't control which enantiomer I get, but I can at least recognize that I will get an anti-addition across that pi bond. So here's another example. If I have a cis-2-butene, I expect the reaction to occur here through the mechanism we just discussed, so I'm not going to show the mechanism again right now. But the outcome of that is anti, right? So if one bromine comes in from the top to form that three-membered ring on top, the other, and that would end up on top in the end, the other bromine would have to come in from the bottom. And it could come in from the bottom on this side, which would give this product here, or it could come in from on the other side, which would give a dash wedge on the other carbon. So I get two different products. There I get anti-addition. Is it possible to form this compound through this reaction? Actually, it is. But you're probably not likely to see it. I can't start with this compound. If I start with this cis-2-butene and I add Br2, I'm only going to get the anti-products. this is an anti-compound, but it's not the anti-product I would get if I start with cis. Right? So what I have to do here is imagine what would happen if this bond rotated. So I'm not changing the structure, just rotating a bond. If I rotate this carbon backbone to look like this, by rotating that bond, so I'd keep this carbon still, I would rotate this bromine and this methyl. So if I rotate this methyl so it comes out of the plane and then up back into the plane here, that would push the bromine down behind and it would end up here. So these two molecules are identical. And so if I want to make this structure, which is the same as this structure, I could do it. I would just have to start with the trans 2-butene. Because if I use trans, then adding the Br2, I would get one bromine to add from the front and one from behind. And I would get this anti-product. So I always get anti when I add Br2 across a pi bond, but I can control which diastereomer I start with that includes the pi bond to make sure I get one or the other stereochemical outcome of the product. Right? So that's the type of thing you might want to look at practicing as well, where you're making sure that you start with an appropriate compound if you want to take advantage of an anti-addition and end up with a specific arrangement of the atoms in the end. So the same two molecules we've been looking at, let's imagine them reacting with Br2 or Cl2. When we do this reaction, a traditional solvent is carbon tetrachloride, and that is because of a reaction we're going to see next semester. I'll just point that out real quick. If you have carbon-hydrogen bonds all over the place, like in my solvent, if my solvent has carbon-hydrogen bonds, there's also the possibility that a Br2 or a Cl2, we'll just call that X2, it can do a substitution reaction for a hydrogen. And that goes through a free radical mechanism that we'll talk about next semester, but you should know it at least to the extent that explains why we're using this solvent, and to the extent where you can recognize that if you see CCl4, that's specifically a solvent for this reaction, because if my solvent had any CHs, which these do not, and this is the reason they do not, if they did have any CHs, the CH could end up being replaced with a chlorine or a bromine. And I don't want my chlorine or bromine reacting with the solvent. I want them reacting with my alkene. So I have to make the solvent unreactive toward bromine and chlorine by making sure it doesn't have any CH bonds. So carbon tetrachloride is a nice solvent. It's nonpolar. It's very polarizable though, so it dissolves a lot of low polarity substances like these hydrocarbons and the halogens as well. And it kind of brings everything together and helps the collisions occur. So the CCl4, I should not see in anyone's exam questions. CCl4 should not be getting involved in the mechanism. It's just a solvent in these halogenation reactions. So the mechanism would involve the Br2 or Cl2 forming that three-membered ring either on top or on the bottom, and then the Br minus or Cl minus comes in from the opposite side to open up the three-membered ring. Right, so again, if the methyl group is blocking the top, I probably expect the three-membered ring with the bromine to form on the bottom to avoid collisions and sterics with that methyl group as the bromine's approaching. And then the other bromine could come in here, or it could come in here. But since this bromine's blocking the backside, it would have to come in from the front. That would give me two different products. They're both anti-products, where one bromine was originally pointing away, and so the other bromine has to come in from the front. That would push the methyl group back, as well as the possibility that the second bromine would come in from this carbon and it would have to come in from the front because the other bromine's blocking the back, and the other bromine would end up remaining in the back with the methyl group pointing out. So these two would be my major products, both of them. I would also get some products that would result from the original bromine coming in from the top. So if that happened, and that bromine came in from the top, it would end up with solid wedges. And that would push the methyl group behind. So then, if the other bromine then comes into this carbon, or this carbon, it would have to do so from behind. If it comes in from behind, that gives me this product. If it comes in from behind down here and ends up with a dash wedge down here, it gives me this product. So even though there are a couple different ways this could happen, I'm still only getting two products. I would not see any molecules forming where the two bromine atoms end up on the same side of the ring. Because if one bromine starts underneath, the other bromine has to come in from the front to open up that ring, so they can't end up on the same side. Same thing here, where the 6-membered ring fused to the 5-membered ring. One of the chlorine atoms could come in from the front, the other would have to come in from behind. So I would have one with a solid wedge and one with a dashed wedge. Likewise, the other possibility would also occur. This one could have had a dashed wedge, and this one could have the solid wedge. But again, I have to have anti-products. I can't form any syn products in this halogenation reaction. Any questions about halogenation? Alright, so should a halogenation reaction be first or second order overall kinetics? Well, the answer there is second order. And the answer comes from the mechanism, right? When we look at the mechanism, what's the slow step? The slow step is the first step. In one step, the bromine collides with the alkene to produce the bromonium ion. That's the slow step. Like, these two are relatively stable. The halogens are not that stable, so that helps things kinetically a little bit, but they're relatively stable compared to this formal positive charge here. Forming that is the slow step. After that, once that's formed, the other Br minus coming in to attack and open up the ring, that's a last step. The ring also has some angle strain and some torsional strain, so this collision helps to alleviate that. So that second step is going to be quite fast and to produce a product. So if we're interested in the order or the rate of reaction, we're really just interested in the slow step and any step that occurs prior to that, which is, since it's the first step here, that's not relevant. So in the slow step, since one molecule of each is needed for the reaction, increasing the molarity of either one of them would increase the rate proportionally. And that means they're both going to be first order. So if I ask you to write the rate law for this reaction, it's going to depend on the concentration of the halogen as well as the concentration of the alkene. And since 1 mole of each is required in that collision, they should both be first order, because doubling the concentration of either one of them will double the rate. And we talked a lot about why it gives anti-addition versus syn, and that's because once one bromine comes in, it's blocking that entire side. The other bromine has to come in from the opposite side, and so one bromine ends up with a solid wedge and the other with a dash. So there's a variation on this reaction that we also want to discuss before we end today, and that's called the halohydrin. So halo for halogen, hydrin for water or hydroxide. So halohydrin, actually we'll just call this hydroxide, is where a molecule adds a halogen and a hydroxide across a double bond. So to do this, I'm going to do very similar reaction to what we just did, which is why I said it's a variation on the reaction we just did, where I add either chlorine or bromine to an alkene, just like we just talked about. But the difference is I'm using water as my solvent. Okay, so in these other reactions we did over here, we use carbon tetrachloride as our solvent. It does not get involved in the reaction. If you see CCl3, it's not a reactant, it's a solvent. If instead I use water as my solvent, it can act as a nucleophile. So when the alkene reacts with the Br2, in the mechanism we just talked about, where the Br2 attacks the alkene and the alkene attacks it back, and this acts as a leaving group, we said that Br minus leaving group is a great nucleophile. So after the three-membered ring forms here, we expect a Br minus to attack one of these carbons and open up the ring. That's how we get two Brs added across a double bond. And that is a good nucleophile, whereas water is a weak nucleophile. So why would water come in here and attack instead of the Br minus? Well, the answer is Le Chatelier's principle, or in other words, the frequency with which those collisions can occur. Because specifically we're using it as the solvent, there's just going to be tons of it around. And the more water there is around, the more the odds are that it will be the partial negative, the nucleophile that attacks here instead of the Br minus. It's just upping our chances that those collisions occur by adding a huge excess of water and making it the solvent for the reaction. So once this bromonium ion forms, if it's water that collides with it first, the water ends up there. And then after that, another water would deprotonate it, and that would produce, again, I'm still getting anti-addition. I still get the groups added across the double bond on opposite sides, because I still have the Br plus blocking that side, and the OH or the water has to come in from the opposite side. So I still get anti-addition, but instead of adding two Brs across the double bond, I add a Br and OH. And that could be useful. There's a lot of molecules where I might want to have those groups attached to then react in some other way, or maybe that's just the final structure I'm trying to make. So why is the bromonium attacked by water rather than Br minus? Because it's the solvent. It's not because it's a better nucleophile, it's because it's just around. As the solvent, it's just much more likely to collide because there's a lot more of it around. When this Br minus leaves, it's not ready, it's not right there, it's not already down there ready to collide. It would probably get quickly surrounded by water molecules and carried away with the partial positive of the water molecules. So it would be free water molecules that are able to come in there and collide more often. So you can do this reaction. As we said, it's finished off by water picking up a proton, and that gives me the halohydrin. Oops. Halohydrin. Hydrin. The halogen and group added across a double bond on adjacent carbons is what a halohydrin is. And so on net, I'm adding a halogen to one side and an OH to the other side, and it has to occur anti, so they're on opposite sides of where the double bond is located. So here's an example of that. We want to analyze the regioselectivity a little bit before we end for today. So here I've got an asymmetrical alkene. If I'm doing a halohydrin, If I'm doing a halohydrin, if I'm forming a halohydrin, I'm reacting a halogen and water is my solvent. So when you see those reactants together, that's the reaction that you want to look for that's going to be carried out. So I have to concern myself with regioselectivity because I want to make sure that the bromine adds to one side and the OH adds to the other side. And since the two sides are not equivalent, I don't have a symmetrical molecule, I want to be able to predict where's the bromine going to end up And where is the OH going to end up? So that's regioselectivity. I also have to make sure I follow the stereoselectivity and do the anti-addition, not syn, S-Y-N, right? We're doing anti. So the mechanism can help me with that. That's why I recommend, even if I don't ask you to draw the mechanism, it might be worth drawing to help you predict the outcomes of these reactions. So in the mechanism, the Br attacks, it gets attacked back. The other Br acts as a leaving group. It gets carried away by water. Since that's my solvent, it will surround it nicely and keep it attracted with some ion dipole attractions. So I form the bromonium ion. I know that that's blocking the top side of this carbon-carbon bond, so the OH, or the water, has to come in from the bottom side. I could imagine it coming in here, or I could imagine it coming in here. Two possible options. So if I'm just looking at this, my prediction, if I'm being honest, I probably would have predicted the wrong outcome, because there looks like there's a lot of steric hindrance over here. Why would the water come in where there's more steric hindrance? Well, what we're seeing here is very similar to something we already saw. What we saw earlier was when I use a mercury, in the beginning we did that Oxymercuration-Demercuration reaction. When I form a three-membered ring with the mercury, if one side's more substituted, I get this resonance situation where the mercury starts to already pull the electrons away from the carbon that can more effectively stabilize a positive charge. It's not going to pull electrons away very much from this primary carbon, because forming a positive there would be really unstable, but forming a positive on a tertiary carbon is not too bad. So this occurs with both the mercury and with the bromine. They're both positive, they both really strongly attract electrons, and so they'll, even before the water comes in or any other nucleophile, before any nucleophile comes in there, I'll end up with a situation where the mercury or the bromine, whichever it is only kind of partially sharing electrons here, and so that flattens things out a little. It creates a large partial positive here, and that's why the nucleophile is more attracted to the more substituted side. It's not because of sterics, it's actually in spite of sterics, because there's still more sterics on this site, but because it has such a large partial positive, because the mercury is already starting to pull electrons away, or in this case the bromine is already starting to pull electrons away, that attracts the nucleophile into the side that has more partial positive. So it's an electronic attraction rather than a steric repulsion that determines which pathway happens more readily in the mechanism. So if the OH attacks there, clearly it's going to end up on anti to the bromine, and we get the regiochemical outcome that we would see experimentally in this case. After the final proton transfer step, I have a halohydrin that's anti, and I get the regiochemical product where the nucleophile ended up attacking the site that carried more of a partial positive during the intermediate and the transition state. And that's what this slide here is explaining. If one side is tertiary and the other side is primary, I expect the nucleophile to attack the tertiary site, and that sounds weird because we said we never ever expect to see an SN2 occur at a tertiary site, and this is pretty much the equivalent of an SN2. The nucleophile is attacking at the same time the leaving group's leaving, but it's not really an SN2, right? In an SN2, the nucleophile doesn't start, or ignore that. In an SN2, the leaving group doesn't start leaving until the nucleophile starts coming in. And if it hasn't started to leave yet, it's too crowded for the nucleophile to attack. So what's really happening here is, before the nucleophile comes in, this has already started to leave. So it'd be better to show it looking like this. The bromine has already started to pull these electrons away, and it creates a large partial positive on the carbon that can stabilize the positive better, which is obviously the tertiary one versus the primary. And so that is the carbon that the oxygen comes in and starts to attack. And that's why we get the specific regiochemical outcome that we showed in the product on the last slide. And if I use a much more sterically hindered nucleophile, maybe that wouldn't be the preferred site of attack because of the sterics, right? So it also helps that the water is a relatively small molecule, so when it does come in, it'll be more likely to come into the site with a partial positive, and sterics won't be as much of an issue. But if I had a much larger nucleophile, that could create an issue. So if I give you a reaction like this, we want to try to predict the outcome. What would happen here? Mostly, as we said, this methyl group's kind of sterically hindering. It's kind of blocking the top a little bit. So the first thing I would expect to occur would be the bromonium ion forming underneath. And then since this side is tertiary and this side is secondary, I expect the water to come in. So I expect this bond to start partially breaking, creating a large partial positive at this tertiary site that can stabilize it better than the secondary. And I expect the water to come in there. Since this bromine's already blocking the bottom, the water has to come in from the front, even though these methyl groups are kind of maybe blocking that side a little bit. There's no other option there. Right, so once this methyl group blocking the top kind of directs the bromine to the bottom, the other bromine, or the water, has to come in from the top due to the bromine of the 3-membered ring totally blocking the bottom side. So when this opens up, this bromine will remain connected here. This methyl group obviously would still be here. The water would come in here. It would have to come in from the top, which would push the other methyl group down. So you can see with this reaction, I can get a pretty specific stereochemical outcome. After the water comes in, it would be deprotonated, and I would end up with an OH there. So that would definitely be the major product. The minor product might also form, so as we said, the methyl is not terribly hindering. So the Br might come in from the top. If it forms a solid wedge here, that would push this methyl group back. And the water would still go to the same side because it's more attracted to the partial positive there, but then it would come in from the bottom since the bromine would be blocking the top. So in that case, the minor product that I might get there would have the bromine with the solid wedge. The water would have to come in from behind if the bromine was blocking the front. So I'd end up with my OH on a dashed wedge, and this methyl group would be pushed forward. So I get two different products. Are they enantiomers or are they what? They're diastereomers in this case, right? So obviously, if some other chiral centers have the same configuration, but other chiral centers have the opposite configuration, that makes them a pair of diastereomers, which is convenient because it's easier to separate diastereomers than enantiomers. I think I'm going to skip this last reaction. We've seen a lot of examples today. If you want to work that one out and share your work with me, I'd be happy to comment on it and discuss that with you individually. So that pretty much wraps things up. We talked about a number of reactions today. So there's a lot there. You want to get used to practicing these in a variety of ways. You want to be able to think about, if I give you the reactants, can you predict a product? If I give you the product, can you come up with a set of reactions that can be used to make it? Can you work through the mechanisms that are involved to make sure you get the right regiochemical and stereochemical outcomes? And there's a lot, obviously, involved in each of those reactions. So please practice up. Please practice up those reactions, and let me know if you need any help. Obviously, we'll be having exam 12 related to this content. Most of you, that'll be next week. The Monday people will be the week after that. So next Tuesday, or next week I should say, as our last week of lecture. Next week we'll be doing day 26 on Tuesday. We'll be finishing up chapter 9 and getting into chapter 10, which deals with alkynes. We haven't really talked about carbon-carbon triple bonds much, so we're going to do that. And then next Thursday we will do day 27, and that will be it as far as new material goes. And so then after that will just be exams and reviews to finish out the semester. So we're getting close. Many of you have been doing excellent this semester. I've been really impressed with how everyone's been handling the pandemic and the remote instruction. the weekly exams. So just finish strong and keep doing what you're doing for the most part. See if you can start to maybe think about reviewing a little bit some of the earlier material to help you prepare for the comprehensive final exam. And check the syllabus for the schedule as we move forward. Feel free to contact me anytime with any questions that you might have.